Now let's see how can we develop a differential formulation, a differential equation from a given physical system. Equilibrium. In the differential formulation, equilibrium and constitutive requirements of a typical differential element is established in terms of state variables, and these equations must be supplemented by additional differential equations that impose appropriate constraints on state variables. Okay. So, for example, let's consider a solid bar and it is loaded quasi-statically with a distributed load Q of x as shown in the figure and a point load F at the right end of the bar. The cross-sectional area of the bar is changing throughout the whole length of the member. Develop the governing differential equation and the corresponding boundary condition. So it's a let's say we would like to analyze this system using continuous system mathematical model. So we have to develop the equilibrium as well as the boundary conditions and these requirements in terms of differential equations. For that, let's consider a differential element in this bar of length dx. So this is the differential element of length dx. So this is the uniformly distributed force in the member Q of x. Let's say the resultant force at the left end of the face of this differential element is represented with F of x, and the force on the right end of this element is represented with Fx plus some change in the force. Now equilibrium of forces in the x direction requires that the sum of all the forces must be equals to 0. So the total force exerted by the uniformly distributed force plus the force on the right face plus the force on the left face, and they must all be equals to 0. And if you simplify this equation, I'll get df over dx equals to minus q, where I know that the force, the internal force f of x, this internal force f of x is nothing but equals to the stresses inside the member times the area over which it is acting. And then from our definitions, the stresses are nothing but equals to the Young's modulus times the strain, and then incorporating the definition of strain, which is the strain in this case it's a strain in the x direction, so it's simply du over dx. So now the force, internal force f of x is equals to E a of x times du over dx. A is a function of x as shown in the figure because the cross-sectional area is also changing along the length of the member. Otherwise, if it's a member of uniform cross-section, so I would have taken simply Ea times du over dx. So now the equilibrium condition, by incorporating f of x in the above differential equation, the differential equation becomes this form. So now this is the equilibrium requirement of differential element, and this equation is not only valid for this differential element for all, but it is also valid for all of the differential elements present in this member. It means that the differential equation which you have developed is not only valid for this differential element but also for the whole body. Okay? So now you can represent the behavior of complex geometry. I mean, it's a irregular geometry. Similarly, if you have some nonlinear material behavior, that can also be represented with the behavior of this one single differential element equation. So you can see that this is the advantage of the continuous formulation, that you don't have the exact stiffnesses and exact equilibrium equations, but you have differential equations which can take into account complex geometries and complex and nonlinear material behavior as well. This equilibrium equation must be supplemented with some other differential equations, which are the boundary conditions. For example, in this particular case, I know that the displacement of this bar is 0 at x equal to 0, and at x equal to L, it is also subjected to some force external force F. So right from this equation I can say that at x equal to L, internal force should be exactly equals to the externally applied force F. So at x equal to L, the internal force must be equal to the external force. So these are the supplementary differential equations that needed to be there in order to solve this equilibrium equation. So this equation cannot be solved without the help of these supplementary differential equations. So now this is the complete differential formulation, or this is the complete mathematical model of a continuous system. So now you have seen that I have discussed the boundary conditions, right? So boundary conditions are actually of two different types. They can be essential boundary conditions or there can be natural boundary conditions. Essential boundary conditions are also called as geometric boundary conditions. In structural mechanics problem, they usually correspond to prescribed displacements, rotations in the body. And from the mathematical point of view, if the highest derivative of state variable is of order 2m, then the order of derivative of essential boundary condition is at most m minus 1. What are natural boundary conditions? So natural boundary conditions are also called as force boundary conditions. In structural mechanics, they correspond to prescribed boundary forces, distributed loads, moments, and the order of derivatives of the differential equations for the natural boundary condition, they are of the order of m to 2m minus 1. For example, for our case of axial bar, the order of highest derivative in the equation is, so this is the equation, and this equation contains dtu over dx square. So the order of highest derivative is 2. So 2m is equal to 2 or m is equals to 1. Therefore, the order of the highest derivative in essential boundary condition must be m minus 1. In this case 0, and I can also see that the order of derivative in this essential boundary condition is 0. And the order of natural boundary condition should be 2m minus 1. So in this case this is equals to 1, and I can also see from our natural boundary condition that the order of derivative is 1. Let's take another example and let's try to develop a mathematical model for this particular problem. Dam on a permeable soil. Formulate the differential equations governing the steady state seepage of water through the soil and give the corresponding boundary conditions. Again, the procedure is same. Take a small differential element in the permeable soil of length dx and dy. Then we can say that the total flow into the differential element must be equal to the total outflow from the differential element, right? So let's say Q denotes the flow in the x direction at the left end, and Qx plus dx is the flow at the right end. Similarly, Qy and Qy plus dy is the flow at each face in the y direction. So now for the typical element, the total flow into the element must be equal to the total outflow. So the total flow in the phi direction must be equal to the total flow in the x direction, and the sum of all these flows, that is into the flow and into the element plus out of the element, must be equal to 0 for equilibrium. And if you simplify it, you will get that this is equals to the change of the flow in the y direction plus the change of the flow in the x direction must be equals to 0. Using the Darcy's laws for the flow and expressing them in terms of the total potential phi, where k is the permeability constant, and I'm assuming uniform permeability. So Qx is represented in terms of total potential with this particular equation, and Qy, the flow in the y direction, is represented by this particular equation equals to minus k times the change in potential with respect to the y direction. Now incorporating these definition of qx and qy into the above equation, I'll get this as the differential equation which is governing the equilibrium requirement of that differential element, or equilibrium of the seepage flow from that differential element. Right? Now we have to supplement this differential equation with some other equations which defines the boundary conditions. We know that there is no flow in the soil at x equals to minus infinity and plus infinity. So at this point and at this point, at x equal to minus and plus infinity, there is no flow into the soil. So change in potential with respect to x evaluated at x equal to minus infinity and plus infinity must be equal to 0. Other boundary condition that the flow because at this particular level this permeable soil is resting over an impermeable rock, so at y equals to 0, the flow in the vertical direction must also be equal to 0, or the change of potential with respect to y at y equal to 0 must be equal to 0. So this is another boundary condition. At the dam soil interface, again I know that for this particular level there is no flow in the vertical direction. So change in potential with respect to y for any values of x and at y equal to L, the flow must be equal to 0, and x only varies from minus h by 2 to plus h by 2, where h is the total width of this dam. So there is no flow in the vertical direction but within this limits of x. In addition to this, the total potential at y equals to L at this region and in this region. So in this region the total potential must be equal to H1, and in this region the total potential must be equal to H2, and this is the mathematical representation that the total potential for values of x less than minus h by 2 means in this zone, for values of x less than minus h by 2 and at y equals to L, the total potential is equals to H1, and for values of x larger than h by 2 and for y equals to L, the total potential is equal to H2. So these are the boundary conditions that can be used in addition to this differential equation for the solution of flow problem in the soil. So all these equations describes the seepage flow in soil medium. So this is now this mathematical model for the seepage flow in a soil. Similarly, in addition to seepage flow, you were also interested to find out the effect of mechanical forces, like what is the effect of the gravity forces exerted by the dam on the soil, how much deformation will take place, how much stresses will take place. So now it is a problem of solid mechanics. So again you can assume, or you can take a general body or okay, in addition to soil you can also let's assume any other generic body. Let's say this generic body is representing it might be representing a house or a building, a bridge, any solid body, right? So it can be soil, it can be a building structure or any other solid structure. Let's say that body is represented with the domain omega. Let's say its boundary is denoted with partial omega. Let's say the boundary at which some boundary forces are applied, which are called as tractions. So they may be uniformly distributed forces or uniformly varying forces, and these traction forces are applied at a boundary represented with partial omega t, and the boundary at which the displacements are restrained are represented with partial omega u. Again, in order to develop the governing differential equation, just take a differential element. If it's a 2D body, take a 2D element. If it's a 3D body, So take a 3D element and then represent forces on that differential element. Excuse me. And then apply the equilibrium condition on this differential element. We have already done it in the previous lecture. So you can apply the equilibrium in the horizontal direction. So the this force plus this horizontal force plus this horizontal force plus this horizontal force must be equals to 0, plus the body forces or the volume forces must be equal to 0. Simplifying it, you will get some equilibrium equation in the x direction. Similarly, apply equilibrium equation in the y direction, and then in the z direction you will get 3 equilibrium equations in 3 directions. You can simplify it and write it down in one generic equation which we have derived it earlier. Partial sigma ij divided by partial sigma j plus bj equals to 0, or in compact notation it can be represented with divergence of sigma plus b equals to 0. So this is the differential equation which is governing the equilibrium of solid bodies. It can be any solid body. And this differential equation must be supplemented with some boundary conditions. So now for this particular example, for this generic body, it can be a bar element like this element. So for this particular case, the boundary conditions are that the displacements are equals to u bar on the boundary partial gamma u, and the forces, the internal forces, are equals to the external forces T bar at the boundary partial omega t. You can compare this equation with the differential equation which you developed for the axial bar, and you will see that these two equations are exactly similar. So you will get dtu over dx square times Ea is equals to minus b. In that case it was minus q, and then you had u at x equal to 0 is equals to 0, and then you had Ea times du over dx evaluated at x equal to L is equals to f. So this is the very generic form of equations of equilibrium and the corresponding boundary conditions for a generic solid body, and it can be applied to any solid body. For relatively simple system, these differential equations can be solved in closed form using techniques of integration, separation of variables, and so on. However, for more complex systems, approximate solution methods will be employed. So in the current lecture, we will discuss those approximate solution methods.